Today we're going to talk a little bit more about multiplication. We're going to talk about multiplying by -1, multiplying by negative numbers in general, and we're also going to show that the square root of 2 is indeed a cut. And it turns out that to do all of the stuff, if we want to do with multiplication, we need the following fact. This is the Archimedean property of the rational numbers. So let's let Q be a rational number, P another rational number, and we're going to insist that P has to be a positive rational number, not zero, not negative, positive. Then there is a natural number that is a positive integer such that minus MP is less than Q is less than positive MP. So the idea is if you've got any two rational numbers, then no matter how small the second one is, no matter how small P is, just by adding it together enough to itself enough times, that is, just by multiplying it by a big enough integer, you can get bigger or small, more positive or more negative than anything you want. And let us prove this. So because they're rational numbers, we can write them as ratios of integers. Q is A over B, P is C over D, where, let's see, A is just any old integer, but our denominators and the numerator of P, the numerator of our positive rational number, they've all got to be positive integers. That is, they've got to be natural numbers. And let's let M, we're going to take the absolute value of A, we're going to multiply it by C, and we're going to add 1. This isn't necessarily the best integer with this property, but it's going to be an integer with this property. Then, so we're going to write negative M times C times B. That's less than or equal to M, because B and C are natural numbers. So BC, the smallest it could be would be if they were both 1. And then, M is A times D plus 1. And then M, and then, let's see, we're putting a minus sign in front of M, and then negative M is negative the absolute value of A times D plus 1. That's less than or equal to AD. Negative the absolute value of A is less than or equal to A, and then multiplying by a positive integer D, and then subtracting 1 certainly isn't going to make you bigger. Then, and a very similar argument. This is less than or equal to M, which is less than or equal to M times C times B. And then we multiply this long chain of inequality is by 1 over BD, and because B and D are both positive, this isn't going to flip any of the inequalities. Negative M times C over D, that's going to be less than or equal to A over B is less than or equal to M times C over D. We're only grabbing this piece and this piece and this piece here. Or then we remember what C over D and A over B were. Minus MP is less than or equal to Q is less than MP. And if you check carefully, you can see that these inequalities, the strict less thans, are indeed strict. AD is less than, strictly less than M. That's why we bothered adding the 1 in here. Okay, now let's have another example. Let's let D be the cut. In lecture 3, part 1. And then D squared equals 2, which, remember, we're saying we identify the rational number Q with the cut that's the set of all rational numbers, Q and Q, such that Q is less than 2. And here is how we are going to prove this. So let's recall what we've got, how these things are defined. D is the set of all rational numbers in Q such that either A is negative or 0, or A squared is strictly less than 2. And we recall multiplication of cuts, D squared. That's the set of all products AB such that A is in D, B is in D, and A is strictly positive. And notice that the A is strictly positive is going to necessarily satisfy A squared less than 2. And we want to show that D squared is just the set of all rational numbers that are less than 2. So let's start with a rational number Q that is not in 2. So Q is, that means Q is greater than or equal to 2. Q is a rational number, and we want to show that Q is not in D squared. So let's let, well, D squared is all these ABs, so let's let A, B, be rational numbers in D. A is greater than 0, so A squared is strictly less than 2. If B is negative, then A is positive, so AB is negative, and 0 is less than 2 is less than or equal to Q, so Q is not AB. So Q can't be in D squared. Q can't be a product of two rationals in D if one of them is negative. So if B is greater than 0, then B squared is also less than 2. That's the only way you can be a positive rational number in D. So let's write q squared. Q is at least 2, so q squared is at least 4. That's 2 times 2. That's strictly greater than a squared. The first 2 is strictly greater than a squared, and the second 2 is strictly greater than b squared. And then in the rationals, multiplication is commutative and associative. So we get that q squared is strictly greater than ab squared. So q cannot be ab in this case either. So in either case, q is not in d squared. All right. Flip side, let's let q be into, that is, q is less than 2, q is irrational, and we want to show that q is in d squared. All right, and this is where we're going to use our Archimedean property. So q is less than 2. So 2 minus q is greater than 0. So this number, 5 over 2 minus q, that is a rational number. We are not dividing by 0. And by the Archimedean property, we have a natural number m, with m is going to be strictly bigger than our natural number 5 over 2 minus q. And I'll point out 2 facts to you. If n is a natural number, n is less than or equal to m, then n over m squared is less than or equal to 1, is certainly less than 2. So in particular, if n is 1 or n is m, then n over m squared is less than or equal to 1, is strictly less than 2. And conversely, if n is a natural number and n is bigger than or equal to 2m, then n over m squared, that's at least 2 squared is at least 4, is strictly bigger than 2. Now what we're going to do is we're going to let n be such that n over m squared is less than 2, but n plus 1 over m squared is not less than 2, is greater than or equal to 2, but we know n plus 1 over m squared cannot equal 2, so it's going to be strictly greater than 2. And if you take a look at the Peano axioms, you'll see that you can prove pretty easily from the last Peano axiom, from the fact that induction works, that there has to be a natural number where n over m squared is less than 2. There's at least one of them, n equals 1, this works. There has to be one where n over m squared is less than 2, but the successor doesn't have this property. N plus 1 over m squared is not less than 2. So, and based on what we said before, n can't be any smaller than m, because if n was smaller than m, then m plus 1 is at most m, so n plus 1 over m squared is at most 1. On the other hand, n can't be as much as 2m. If it was, n over m squared would be at least 4. And I want to say a little bit more about this n plus 1 over m squared condition. We're going to multiply out the numerator. N squared plus 2n plus 1 over m squared is greater than 2. So n squared over m squared, that's greater than 2 minus 2n plus 1 over m squared. M is a positive integer. It's at least 1. N is less than 2m, so this is certainly greater than 2 minus 2 times 2m plus m over m squared, also known as 2 minus 5 over m. And if we go back to our definition of m up here, you can do a little bit of algebra and see that this is true if and only if 2 minus 5 over m is bigger than q. So we've got a rational number n over m, and its square is between 2 and q. So q we're going to write as n over m times q over n over m. And notice that that is a product of two rationals. N over m is a rational. It is positive, and n over m squared is less than 2. So n over m is in our cut D. N over m is positive. So we're going to let n over m be the number, be our number a in the formula for D squared. That satisfies all the properties of our a in our formula for D times D. Right, now let's think about this second piece, q over m. So if q is less than or equal to 0, then q over n over m, that's also negative because n and m are both positive. So b of course is q over n over m is in D. So q is in a times b, where a is in D, b is in D, a is positive. And if q is greater than 0, well, we already promised ourselves that q is less than 2. So we can write that this way. Then b squared, that's q over n over m squared. That's q then times q over n over m. And then remember we said q was less than n over m, squared. So this is strictly less than q, which is strictly less than 2. So b is in D in either case. So q equals ab A and B are both in D, and A is positive. And that completes the proof. That establishes that D squared is precisely the Dedekind cut of all the rational numbers less than 2. So the square root of 2 is a rational number. This number we were talking about, we were so worried about it not being around. That does work out for us. Okay, in this video, what we're going to do is we are going to talk about multiplication some more. Now, we wrote down the definition of what it means to multiply two Dedekind cuts that represent positive real numbers, two Dedekind cuts that are bigger than 0, that have some positive rationals in them. We would also like to be able to multiply negative numbers or negative times positive, that sort of thing. And it turns out most of the work is going to be multiplying by -1. So let's write down this proposition from your book. Let's let alpha be a Dedekind cut, a real number. There is another Dedekind cut at another real number, such that alpha plus beta equals 0. And we are, of course, going to view beta as -1 times alpha. So let's think about this for a moment. So if alpha is the set of all rational numbers that are less than, let's say, 3, then beta we're going to write as the set of all rational numbers that are less than -3. Yeah. So remember, we're identifying the rational number 3 with our alpha, the rational number -3 with this beta, and we really do want multiplying by -1 in the sense of real numbers to be the same as multiplying in the sense of rational numbers. So this is what you do if your cut alpha is one of the cuts that's secretly a rational number, but what if it isn't? Well, let's think about this for a moment. Let's give ourselves a number line. So here is our cut alpha. We start at 3. We go down to -infinity. Here is our cut beta. Let's use a different color. Here is -3, and then we go down to -infinity this way, and then halfway in between them, we've got 0. So this picture is what we're generally going to want. We're going to want Dedekind cuts that are symmetric about 0. So let me also point something out to you. So here is our beta, here is our alpha, and then if you take everything that's in beta and you multiply it by -1, you end up here. This is the set of all -q with q in beta. So alpha and this thing I've drawn in yellow, they have almost all the rational numbers in them, except you want to be missing this one little point 3. This one point, if it's So here is how we are going to prove this. Here is the general formula for beta. So we're given alpha. It's not necessarily the rationals less than 3 anymore. That's the example. So now we get to define beta. We're going to let beta be the set of all negative q such that q is not in alpha. So that would be picking up all of these guys up here, except we'd also pick up this thing. We'd end up trying to have negative 3 be an element of beta, and that's no good. So we want to make sure that that's not true. So we're going to specify that R is not in alpha for some R less than Q. And that kind of means this Q less than alpha condition is redundant. We don't really need it. So here it is on the picture. Here is our Q. Here is our R. And then here is negative R. And here is our negative Q. And this complication, this bringing in this number R, is precisely to take care of this case where alpha is a rational number, to make sure that when you flip it around, you get a cut. All right, so we need to check. So what is it we want to show? A WTS stands for want to show. We want to show beta is a cut and alpha plus beta equals 0. So let's go through our conditions of a cut. I guess we would need to specify that Q is indeed a rational number. But if we remember to specify that beta is a subset of the rational numbers, let's see, alpha is not equal to all the rational numbers. Let's let R not in alpha, then negative Q is in beta for all Q bigger than R, and rational numbers you can always get a bigger one. So beta is not equal to the empty set. Similarly, alpha is not equal to the empty set. We're going to let P be an alpha. Then R is an alpha for all R less than P are a rational number. Suppose we do need to specify that explicitly up here too. So negative P is not in beta, so beta is not equal to the set of all rational numbers. And if Q is in beta and P is a rational number that is less than Q, then we have that there is a R that's a rational number but not in alpha, R is less than negative Q, which in turn is less than negative P, so P is in beta. And finally, if Q is in beta, so negative Q is greater than R for some R that's a rational number but is not in alpha, then this number, negative Q plus R over 2, it turns out if you take the average of two rationals, you always get a rational that's between in them. That's not too hard to check. This is negative Q plus 1/2 of negative Q minus R, or minus 1/2, sorry, and this part is greater than 0, so this is certainly less than Q, but it is also equal to R plus 1/2 of negative Q minus R, so it's certainly greater than R. So negative Q, so let's let, so P, let's write that as Q minus R over 2. Negative P is less than Q, so this satisfies. Q is less than P. Negative P is still bigger than R, so our P is in beta. P is bigger than Q, so beta is a cut. All right, so now we have shown that our beta is indeed a cut. So now we just need to figure out what alpha plus beta is equal to. All right, so alpha plus beta is the set of all P plus Q such that P is in alpha, Q is in beta. So we need to show that this thing is equal to 0, that is, it's the cut that's all the negative rational numbers. So let's pick P in alpha, Q in beta. And then negative Q is greater than R for some R that is not in alpha. So that means that negative Q is greater than R is greater than A for all A in alpha. So in particular, negative Q is greater than P, and adding Q to both sides, 0 is greater than P plus Q. So alpha plus beta is a subset of the cut 0. That's the set of all all of the negative rational numbers. All right, conversely, we're going to go ahead and let x be in 0. So x is a rational number. X is a negative rational number. And our goal is to show that x is in alpha plus beta. Right, so now here's how we're going to do this. We're going to let y be negative x over 2. So y is a rational number, a positive rational number. And we're going to let a be strictly less than x, and a is so in alpha. And alpha is half infinite, so you can go down as low as you like. So I'm allowed to insist that I want a to be less than x. All right, then actually, let's go ahead and make a less than x minus y even smaller. And we're going to let k be the set of all natural numbers such that a plus n times y is in alpha. All right, and notice, so 1 is in k, but by the Archimedean property, let's let s be a rational number with s not in alpha, and then by the Archimedean property, we've got that n times y is bigger than s minus a for some n. So k is not allowed to be all of the natural numbers. There's one where this n we just wrote down, a plus ny, is bigger than s, so it can't possibly be an alpha. If it was an alpha, s would have to be 2. And so by the last Peano axiom, there has to be a natural number n in k whose successor with n plus 1 not in k. So we're going to let P be a plus ny, and then P is in alpha by definition. And we know that a plus n plus 1 y is not in alpha, so p plus y is not in alpha. So now p plus 2y is greater than p plus y, our thing that's not in alpha, and everything inside it is rational. A is an element of alpha, so it's rational. Y is half of negative x, so it's rational. P is a rational plus an integer times a rational, so negative p plus 2y is in beta. So p plus negative p plus 2y, that's p minus 2y, that's minus 2y, that's x, is in alpha plus beta. And remember, x was an arbitrary element of 0, so that So we've got that 0 is a subset of alpha plus beta, and we saw before the reverse inclusion, so 0 equals alpha plus beta, and we are. In the last video, we saw how to define negative multiplication by -1. So recall the proposition from the last video says that if alpha is in R, there is we called it beta, but now we're going to call it negative alpha in R, such that alpha plus negative alpha is equal to 0. And then just clearing up a little bit of notation around multiplication. So here is proposition 1.2.22. This isn't too hard to prove. We're going to let alpha, beta, and gamma be real numbers. So the proof of this is an exercise. So first part is the map, or should I say the function that sends each alpha to negative alpha is well defined. So it is a function. So that is, if alpha plus beta equals alpha plus gamma equals 0, then beta equals gamma. And this actually follows pretty easily from the fact that inverses exist and addition is commutative and associative, and adding 0 doesn't change things. So if I say negative alpha, there's no possibility that there's more than one of it. There's one real number that's negative alpha. Then part B is that this map, if you take negative alpha, you get alpha back. So being additive inverses is a symmetric property. And then property C is that if alpha is positive or non-negative, then minus alpha is negative or non-positive. And it's a simple consequence of part A and part B that if minus alpha is minus beta, then alpha is beta. And it's also pretty straightforward to show that minus 0 is 0. All right, and then once we've got multiplying by -1 under our belts, it is not too hard to multiply yet arbitrary numbers, arbitrary real numbers, since we can multiply by -1 and we can multiply positive numbers. So first case, 0 times multiplying by 0 indeed gives you 0. Second case, if alpha is positive and beta is negative, then alpha beta, that's negative. You take alpha and negative beta is indeed positive, so alpha beta is minus alpha times minus beta. The right-hand side is well defined, so that's how we know what the right-hand side is. So we've got a left-hand side. Similarly, if alpha is the -1 and beta is the +1, then we define alpha beta to be minus alpha times beta. And then, last case, if they are both negative, alpha beta is just minus alpha times minus beta. And so that's how you define multiplication. Having a bunch of cases like this is annoying because there's a lot of stuff to check when you're proving that multiplication is associative and commutative and so on, but nonetheless, you can do this. You can carefully check proposition 1.2.25. You can check that everything still works, even if alpha and beta and gamma are allowed to be negative or zero, except of course for this one. This is true if alpha is positive, and if alpha is negative, then alpha inverse. It's the same trick. You take negative alpha, so it's positive. You take the inverse, and then you take the negative of that also, and that is going to satisfy alpha inverse equals 1.